Hi people, we are back. After a short break to fix some technical glitches, the No-Protractor Ray Diagram series is finally back in action. Today, we aren't just drawing, we are decoding concave mirror. Most students struggle with accuracy, but I'm going to show you how to draw two complex diagrams back to back with perfect precision. Buckle up, this is the masterclass you have been waiting for. Let's start with the principal axis. Watch closely. I am aligning the edge of my ruler perfectly with the line on this ruled page. Now, draw a dotted line exactly 6 cm long. Mark dots at the 1 cm, 3 cm and 5 cm marks. Why these specific numbers? It's the golden ratio for your notebook. It ensures your diagram is large enough to be clear, but small enough to fit perfectly in your margin. Notice the arrows at the ends? We treat this exactly like the x-axis in a Cartesian system. And yes, it's dotted because, in physics, this line is an imaginary guide, not a physical entity. Time for the compass. Place your needle at C and draw an arc through P. Remember, this arc is a 2D slice of a 3D sphere. We shade the bulged out side because, in a concave mirror, the reflection happens in the cave. Let's send in some light rays. Use the lines on your page to ensure the rays are perfectly parallel to the axis. Watch what happens after reflection. They all converge at that 3 cm dot. These rays don't stop there, they keep going. Draw them past the point and add your arrows. Labeling time. X prime for the axis. X prime being the leftmost point, X being the rightmost. P and C are also labeled. F, principal focus for that 3 cm mark. The logic, theoretically, F must be the midpoint of CP. Since our CP is 4 cm, from 1 to 5, our focus sits perfectly at the 2 cm mark, which is our 3 cm dot. Precision achieved. Now, let's level up. A little out of the book knowledge for the CBSE Class 10 champs. What if the rays are parallel to each other but not to the principal axis? Recreate the setup. I am drawing the first ray intentionally through the principal focus and making it incident at a point where a line on the page intersects the mirror. Why? We'll see later. Since these rays are oblique, we can't use the page lines. Align your ruler so the major markings stay perpendicular to your first ray. This makes the edge of the ruler perfectly parallel for the next rays. Clever, right? Now, draw a dotted vertical line through F. In your 2D notebook, this is a line, but in the real world, this is the focal plane. The rule of symmetry. A ray parallel to the axis passes through F after reflection. Therefore, a ray passing through F must become parallel to the axis after reflection. I intentionally drew my first ray through F so that after reflection, it travels perfectly along this ruled line of my page. Where this ray hits our focal plane is exactly where every other parallel ray will converge. Now, let's talk about the focal plane. All the points on this plane are foci. This means whenever a parallel beam of light, whether parallel to the principal axis or not, is reflected by the mirror, it converges on a point on this plane. Principal focus is special amongst these innumerable foci as it lies on the principal axis. Each of the other foci is called a secondary focus. Here, the secondary focus is labeled as F1. There you have it. All the key features of a concave mirror explained through pure geometry. I'll be back soon with the next set of diagrams of concave mirror. Until then, keep building, keep drawing. Bye.